Correct. The answer is logarithm, because logarithm has this very nice identity that says that the logarithm of the product a times b is the sum of the logarithms of a and b. So this is what we do. We take our products and we take the logarithms. So now we get a sum of the logarithms of the factors. So the logarithm of 0.6 times 0.2 times 0.1 times 0.7 is equal to the logarithm of 0.6 plus logarithm of 0.2 plus logarithm of 0.1, etc. Now, from now until the end of the class, we'll be taking the natural logarithm, which is base e instead of 10. Nothing different happens with base 10. Everything works the same, as everything gets scaled by the same factor, so it's just more for convention. We can calculate these values and get minus 0.51, minus 1.61, minus 0.23, etc. Notice that they are all negative numbers, and that actually makes sense. This is because the logarithm of a number between 0 and 1 is always a negative number, since the logarithm of 1 is 0. So it actually makes sense to think of the negative of the logarithm of the probabilities and we'll get positive numbers. So that's what we'll do. We'll take the negative of the logarithm of the probabilities. That sum of negatives of logarithms of the probabilities we'll call the cross entropy, which is a very important concept in the class. If we calculate the cross entropies, we see that the bad model on the left has a cross entropy of 4.8, which is high, whereas the good model on the right has a cross entropy of 1.2, which is low. This actually happens all the time. A good model will give us a low cross entropy, and a bad model will give us a high cross entropy. The reason for this is simply that a good model gives us a high probability, and the negative of the logarithm of a large number is a small number, and vice versa. This method is actually much more powerful than we think. If we calculate the probabilities and pair the points with the corresponding logarithms, we actually get an error for each point. So again, here we have our probabilities for both models and the products of them. Now we take the negative of the logarithms, which gives us sum of logarithms, and if we pair each logarithm with the point where it came from, we actually get a value for each point. And if we calculate the values, we get this. Check it out. If we look carefully at the values, we can see that the points that are misclassified has large values, like 2.3 for this point or 1.61 for this point, whereas the points that are correctly classified have small values. And the reason for this, again, is that a correctly classified point will have a probability that is close to 1, which when we take the negative of the logarithm will get a small value. Thus, we can think of the negatives of these logarithms as errors at each point. Points that are correctly classified will have small errors, and points that are misclassified will have large errors. And now we've concluded that our cross entropy will tell us if a model is good or bad. So now our goal has changed from maximizing a probability to minimizing a cross entropy in order to get from the model in the left to the model in the right. And that error function that we're looking for, that was precisely the cross entropy.